more expensive than making them at room temperature. And a lot of what we're going to be doing over the next 5-10 years in terms of this mission is having debates about, is it worth it to go out here if it's at the potential risk of more cost in order to get these methane observations? If not, what else could we do? So take home point number 2, if I want to confirm, if I want to be as thorough as I can, I want to get information about the star and I want to look for methane. Methane and oxygen together, still a great biosignature. Methane and ozone together, still a great biosignature. Methane without oxygen, oxygen or ozone without methane, not nearly as strong. But methane's hard to detect, so what else could we do? Well, if we don't have one mechanism to rule out all of these, a sort of a skeleton key to rule out all of these false positive mechanisms, we can rule them out one by one. And basically what this entails is going after specific gases. If CO2 is being photolyzed to form CO and O, and then O is recombining to form O2 and O3, well, let's look for the CO2, and let's look for the byproduct of that process in terms of the CO. These are things where if this process is efficient enough to form oxygen, it only will happen basically if the CO2 is itself abundant enough to be detectable. Likewise, in this case, we're going to get a massive oxygen atmosphere that has much more oxygen in it than our modern day atmosphere. That's going to bring about different spectral features than modern day Earth. And similarly, this kind of atmosphere would have no pressure, because the way you avoid getting the cold trap is you don't have a non-condensable gas. So for us, we have nitrogen. Most of our atmosphere, most of the gas you're breathing in is nitrogen. The pressure imparted by the nitrogen is part of the reason we have a cold trap on Earth. So if you don't have that, that's how you form the lack of a cold trap that lets water get up into the upper atmosphere. So one thing you want to do is try to get an estimate of what the pressure level of the atmosphere is. And now these also have their own spectral features. Okay, I'm actually gonna, CO2 has spectral features here and here and here. You don't actually have to go all the way out to 2.5 microns where you worry about the temperature of the telescope. For the massive oxygen atmosphere that comes from hydrogen loss, you have, I mean, this is the line here for like an Earth-like planet, it's this one, and these yellow and white lines are for the ones with the more abundant oxygen concentrations. They just don't look anything like Earth. No one would look at these spectra and say, oh, there's life there, this is just like Earth. It is, and to my eyes at least, when I look, because I looked at a lot of these things, this is an alien planet, it's not like Earth, it's not something I would call the president over. Without going into the details on it, it's kind of busy. So take home point number 3, there's a number of features that would indicate a false positive, and all currently known abiotic oxygen and ozone production mechanisms have something that would be identifiable with a wavelength range that would not necessitate a super expensive, super cold, super large, super starlight suppressing telescope. It still need to be super large and starlight suppressing, but at least it wouldn't have to be cold anymore. Okay, so now let's just do fun games like this. Now I made this like, I gave a talk similar to this a week ago, and I made this like at 1 in the morning right before that talk. So this is just my opinion. This hasn't gone through like any formal NASA process or anything like that. But this is basically like a logic, we can start to put together a logic flow chart for how we might do the observation, right? We might say, you know, okay, let's look at the star system and look for, first of all, is there a lot of like background images? Because Hubble's found all these like galaxies and stars that are very dim. And we're going to block out the starlight and look for a very, very dim planet, but it might be that in that part of the sky there's background galaxies and stars that sort of swamp our signal. So if there is a lot of that, that's not a bad thing necessarily for science, it's just a bad thing for the science I want to do with it. So we hand that image off to the cosmologists that look at galaxies and stars, let them do their thing, and then we move on to the next target. So we search for the planets. If it's not full of background stuff, we search for planets. If it doesn't have planets, we try to do some other imaging with the disk. Again, hand it off to my colleagues that do that kind of science, let them do their thing, and then move on to the next target. If it's got a rocky planet in the habitable zone, okay, then I want to get that low resolution, low resolution spectrum. That can tell me if the planet has water. Okay, if it doesn't have water, I'm not too worried about it, at least from the astrobiology and the search for life standpoint. If it has water, I get a higher resolution spectrum. This is just getting more, better information on what gases are in the atmosphere. That would let us look for oxygen. We have oxygen. Then I start ruling out these false positives, and eventually you flow down. You know, does it have lots of O2 and therefore the O4? No. We go into the longer wavelengths and look for the methane, and then if it has the methane, I cork the champagne and it's higher. And again, there's sort of If it doesn't have methane, we look for these other false positive mechanisms. And eventually, I'm trying to always get back to the champagne and the retirement part of it. But you know, I should also say I've made this as if we were like sort of being pathological and just looking for life and not doing any other science with the telescope. In reality, this telescope's going to do a lot more science, first of all, for exoplanets, because the things we find on these other worlds, separate from the search for life beyond Earth, are going to tell us a ton of planetary science information. We've already learned